In a series of lectures, we shall discuss the techniques for numerical integration. Let me first differentiate between numerical integration, between numerical integration and analytical integration. Consider a function f of x whose graph is given like this. It is f of x is a continuous function, and our aim is to evaluate it between x is equal to a to x is equal to b. So our problem at hand is to evaluate the integration between f of x dx between a to b. If we know the form of the function, then we can evaluate it exactly by using mathematical formulae. As for example, x to the power n dx from a to b is known to be 1 upon n plus 1 b to the power n a to the power n. This we call it exact or analytical result. There are many functions for which the analytical result of integration exists and they are available in text. But if the function under consideration is too complicated, then we may not although we know the form of the function, but we cannot calculate it by analytical methods. Another type of problem arises is that we do not exactly know the function, but we know its curve, or the curve of the function is known, or we may have few discrete x and the corresponding y data. That is to say, we are only provided with few data points. Then how to calculate the value of the function integration between a and b? These are the problems of numerical integration. So numerical integration comes into play when such integration cannot be calculated in closed form. The inability to calculate it in closed form may arise from a few points. When the function f(x) to be integrated, that is the integrand is too much complicated, then the analytical although the function is known, the analytical technique fails. And sometimes it so happens that the function itself is not known, but we are provided with few data points. Few data points means, say we are provided with a set of n plus 1 x and y data. Then we are to find out the value of the function, value of the integration between the limits x0 is equal to a to xn to b. This is the technique of numerical integration. Firstly, we shall discuss two numerical formulae for the evaluation of a definite integral, which is known as the trapezoidal rule and Simpson 1/3 rule. In trapezoidal or Simpson 1/3 rule, we divide the interval a to b into n equal intervals. So a to b, this interval is divided into n equal intervals of width h is equal to b minus a by n, such that if we define x0 is equal to x0 plus ih, then x0 is equal to a, then x0 is equal to a, and xn is equal to b. And there are n such divisions. What one does, once calculates the area under the curve, and one defines the definition of integration, definite integral f of x dx from A to B is equal to area enclosed by f of x with x-axis with the x-axis between x is equal to A to B. This is the definition that we use for the evaluation of definite integral. So we divide this area of the range A to B into n equal strips, each of with h, and then we calculate the area under the curve, and we say that the sum of these individual areas gives us the value of the integration of the function between the limits A to B. Now the question arises, how do I estimate the curve? Let us consider a situation that this is the these are the two consecutive values. Say this is the xi value and this is the another value xi plus 1, and we are to estimate the function between xi to xi plus 1. In the simplest case, we replace this exact curve by a straight line connecting these two y values. Obviously, in that case, the resulting quadrilateral is a trapezoid. And corresponding rule is called the trapezoidal rule. So let me remind you once again, we divide the entire interval into n equal strips, each of with h, such that xi is this, and for two consecutive x values, between two consecutive x values, the curve may be different, but in the first approximation, we replace the actual curve by a straight line. In general, the curve between two values of x may be approximated by a polynomial of higher polynomial, and the polynomial is called the integrating polynomial. So first let me introduce what is integrating polynomial. The actual curve by a polynomial called integrating polynomial. For n of x, if n is equal phi m of x, m, it is a polynomial of degree m. If m is 1, that is, it is a constant function, then the corresponding formula is called the trapezoidal rule. That is, the actual curve between two consecutive values of x are approximated by a straight line. So phi m, where where phi m of x is a polynomial of degree m. If m is equal to, if we have m is equal to 1, then phi m of x is equal to constant a0. The resulting rule is called trapezoidal rule. If m is equal to if m is equal to 2, phi m of x is equal to a0 plus a1 x plus a2 x square. This is that is the value between two consecutive x values are approximated by a parabola. It is a straight line. It is Simpson 1/3 rule. 1/3 rule. This is a parabolic pit. If we put n is equal to 3, we get it as a0 plus a1 x plus a2 x square plus a3 x cube. This gives you Simpson's 3/8 rule, and the pit is cubic pit. So in this way we can go on integrating the degree of the polynomial, integrating polynomial, but it is found that by merely increasing the degree of the polynomial, the satisfactory results are not obtained always. Another point that is to be kept in mind in numerical integration is its convergence. This is a problem that we have never encountered in analytical integration, because analytical integration we get the result in closed form, but in numerical integration we basically get the result as the area under the curve by dividing it into n equal points. Now if the say we divide this interval into 100 equal points and get the result in that is I100, then we increase the n value to 110 and we get the corresponding result I110. So we take the difference. If this is less than the accuracy level, that is we want the result to be correct up to say third decimal place. So if the modulus value of these two is less than 0.0001, then we say the result is convergent. If not, then we say go to I120 and take the difference this, and if the condition is satisfied we stop there, otherwise we go for the next iteration, that is we increase the n value further. That is to say, in numerical integration the convergence is tested by first evaluating the value of in the integral with n subdivisions, then we change n values to delta n and check whether in delta n minus in is less than epsilon. If yes, stop. If no, we set n is equal to n plus delta n and go there. Sorry, and go there. And we carry on this process repeatedly. This is the basic algorithm of any numerical calculation. We shall first develop the theory for the process, and then for the methods, and then at the end we shall discuss the corresponding algorithms. First, in trapezoidal rule, the integrating polynomial is a linear one. So we write phi 1 is equal to a0 plus a1 of x. Now we divide the entire interval into n equal steps. This is A, this is B. So h is equal to b minus a by n for a given n, and as we increase the value of n, the width size decreases, and we write xi is equal to a plus ih. Now we consider a strip, this strip, ith strip. This is xi and this is xi plus 1. So the area, this area we call AI. Basically, the integration in that we are considering is the integration of fx dx between these limits is the area under the curve AI. So I is equal to 0 to n minus 1. This is the area. We are approximating basically this area in trapezoidal rule, where AI is the area of the ith strips which has lower boundary xi and the higher upper boundary xi plus 1. So to say, AI is fx dx between xi to xi plus 1 had it been exact one, but in trapezoidal rule this is being replaced by phi 1 of x dx, which is equal to a0 plus a1x integration dx from xi to xi plus 1. This is equal to integration a0 plus a1x dx between limits xi to I plus 1. And the result is, this approximate result is a0 x plus half a1 x square within limits xi to xi plus 1. This is a0 xi plus 1 minus xi plus half a1 xi plus 1 square minus xi square, this is equal to xi plus 1 minus xi a0 plus half a1. Here we have divided it a square, you have used a square minus b square is equal to a plus b into a minus b. Since this is equal to h times a0 plus a1 xi h by 2, as xi plus 1 is equal to xi plus h. So this difference is simply h. This is a1, this is twice xi plus h, and 2 has been taken adjusted with it, so this is the result. So to say, if we assume this particular form of the integrating polynomial, the corresponding area ai is this. Our aim is to express this result in terms of yn and yi plus 1. Now we consider yi. Yi is equal to f phi 1 at xi. This is equal to a0 plus a1 xi, and yi plus 1 is equal to phi 1 at xi plus 1, which is a0 plus a1 xi plus 1. If we just add these two, we get twice a0 plus a1 xi plus 1. If we take 2 common, we get a0 plus half this part is exactly this one. So we can write it as h by 2, this part h by 2, and the rest part within the third bracket can be written as yi plus 1. So this is the area of the ith block. This is called the block formula for trapezoidal rule. This is called block formula. That is the formula which evaluates the integration under the suitable approximation or under the specific approximation for a particular block. That's why it is called block formula. The composite formula is obtained by adding up the adequate number of blocks. So with this we come to composite formula. The composite formula this is the area under the curve. It is, as I have defined, it is 0 to n minus 1 ai, and for ai I write in trapezoidal rule this is h by 2, which is constant, taken out. I is equal to 0 to n minus 1. This is yi plus 1. If we write it in longhand, this you see for the first part h by 2 is common. That first part y0 plus y1, this is for the first block or 0th block, 0, then y1 plus y2 and right up to yn minus 1 plus yn. You see that the first and last values occurs once and all other values occurs twice. So the result is y0 plus yn plus twice y1 y2 right up to yn minus 1. This can be written in summation notation as and furthermore you note that y0 is the value of the function at x is equal to a, yn is the value of the function at x is equal to b, and yi is the value of the function at xi is equal to f of a plus ih. So this is the formula for trapezoidal rule, in which the integrating polynomial is a linear polynomial. As it is evident that if we have the function which has much ups and downs, then if we want to integrate it by, if these be the two consecutive points and we integrate it by a straight line, then we may not get good result. In which case, by increasing the number of points, we may have an improved result, but it is not guaranteed that by increasing the number of points will get adequate result. As for example, if we go on increasing n values, there are integrands for which the trapezoidal rule does not give a convergent result. By convergent result, we mean that as we go on increasing n values, starting from n and changing the n values at each steps by delta n, that is, each start with n and then we increase n to n plus delta n. If the accuracy is attained, fine, otherwise this value is replaced and we go on increasing n values in steps. And after certain iteration, if we find that the value of the integration between two consecutive n values are less than the desired small number, then we say the result is accurate. The convergence has achieved. And if this fails, then one way is to go on increasing n values. And when by brute force, by going on increasing n values, we do not get the desired accuracy, we say the method fails for the integrand under consideration. In the next class, we shall consider the Simpson 1/3 rule, in which case the integrating polynomial is a parabola.